Okay, so let's take our quick look at the calendar. You guys turned in the take-home quiz last class. I didn't have a chance to grade them yet, so I'll hand them to you next class on Monday. Today is a pre-calc review day in preparation for a calculus day where we talk about the derivatives of inverse functions, and in particular the derivatives of log functions. So that's coming next time, but today is no calculus, only a pre-calc review. Important for you guys is that the steel drum project is due on Monday, and then rapid fire pipeline project is due Wednesday. All right, so hopefully we've made good progress so far, and we're winding these things down. If you are available to get into a study group this weekend, maybe make plans with some of your partners here today during the activity period to meet and see if you can churn through as much of both of those as possible. Then coming up a week from today is our review day for test number 2, which is happening Monday, a week from this coming Monday. Okay? Questions on the schedule? And then what happens on the next class after the test? Rainbows and data, 2 new projects, the last 2 math projects of the semester. Okay? All right. Yes? So not quite 2/3 of the way through, because after test 3, we have, looks like about 5 or 6 classes. We're getting there. Yeah, I mean, the class numbers give you a good indication. So today we're on class 21, and there are a total of 42 altogether. So today is exactly halfway. Reflection is a project where you will look back on the semester. So it is a 7th project, but you won't be doing any math. You'll just be reflecting on what you accomplished this semester. Any other questions? All right, so let's jump in on page 37. We'll start up here at the top with Cameron. Okay, so let's take a look at number 1, which is an old AP question. AP is the advanced placement exam that some people take. There's a calculus version, and this is from an old question. It says f of x is x over x plus 1, then the inverse function, and then there's the symbols for the inverse function, f to the -1, which is read f inverse, is given by, and then we've got a multiple choice question here. So we've got to figure out which one of these is the inverse function. So forget about the choices, but let's just go through this process quickly that I think you'll recognize once we start it. So I'm going to recopy the function, but I'm just going to call it y instead of f of x. I'm just changing the f of x into a single letter. And then the key idea is that when you go from a function to its inverse, the input and output swap. And so all we're going to do is exchange all the x's for y's and the y for an x. So this becomes x equals y over y plus 1. And then to find the inverse function, what are we trying to solve for? We're trying to solve that for y. So let's multiply both sides by the y plus 1 to get rid of that denominator. And the thing that's awkward here is that we're trying to solve for y, but y appears in 2 different places. And we got to get those y's groups together. So first we have to unbury the y from the parentheses that it's in. So how do we do that? We'll distribute that x. So it becomes xy plus x equals y. And then we're going to move both terms with y's in it to one side. I'm going to move them to the right side. So subtracting that xy from both sides gives me x equals y minus xy. So far, so good. And the whole idea of getting the y terms on one side and the non-y terms on the other is what can we do now on the right-hand side? There are y's in every term on the right-hand side. So what can we do? We can factor that y out. That's the key. That's what makes this idea work, is that if you factor out that y, then you took an equation that had 2 y's in it and traded it in for an equation that had just a single y in it. That's the key. And now solving for y is just about done. So we'll divide both sides by the 1 minus x. So we get y equals x over 1 minus x. And that's our answer. The last step is to maybe replace that y right there with what have we really found here? What is this? That's the inverse function. So let's call it f inverse of x. So it looks like choice C. Questions on the process for finding the inverse of a function? You've done this before, yes? Okay. Some people don't swap the x and y in the beginning, but they just solve the original equation for x, and then they swap the x and y at the end. It's equivalent. So whatever is familiar to you, you can do. Okay, let's move to number 2, which asks us if we know what these statements mean, y equals log base b of x. So we haven't really talked about logs this semester. So this y equals log base b of x is equivalent to some equation with an exponent in it. So does anybody know where the pieces go in the other equation? E to the y equals x, that's it. And essentially it's just something you memorize. I mean, you might have seen it kind of derived in some previous class, but the idea is you just take that base, raise it to that power, cross the equal sign, make it equal to the thing that's inside the log. And so just as a quick example here, like if I said log base 2 of 8, and I want to know what that's equal to. So I'm just going to write the answer and then we can confirm. So I claim that this is equal to 3 because, so if we follow this kind of purple arrow pattern, what to the what equals what? 2 to the third equals 8. So because we believe 2 to the third equals 8, it must be true that log base 2 of 8 is 3. Okay? So that's the basic idea behind logs. And there are 2 bases that are really special. I chose base 2 here, but that's not one of the ones we usually use. So if you just see log of x and there's no base supplied, what base is implied? That's 10. So I'll put a little 10 there that's invisible, and then we'll follow Cameron's same purple arrow idea. So what to the what? 10 to the y equals x. That's the corresponding exponential equation. And then if you see ln of x, again, it's a special base. What's the base in this one? It's e, that magical number that we talked about a couple classes ago. So that's a base e, which means that what to the what? E to the y equals x. Right? So log base 10 and log base e are so important that we have buttons for both of them on the calculator. Log base 10 is called the common log, and log base e is the natural log. Natural logs, that's what the L and the N stand for. Natural log, it's in Latin, so it's reversed. Okay, let's try number 3. We'll go to Andy.
For log of 800, guess the value of the expression. Use your calculator, find the value of the expression, and then write a valid exponential equation that relates to the expression. And the answer.
Okay, so let's try this one. So log of 800, we're going to type it on the calculator, but first I just want to test our intuition and understanding of what that means. So log of 800, let's just give it a name here. I'm just going to call it y, just so I can name it. And again, what's the implied base? Is 10, and so then the corresponding equation here is what to the what? 10 to the y equals 800. So again, don't use a calculator just yet. But for example, 10 to the first is 10, which is too small. 10 to the second is 100, which is still too small. 10 to the third is 1,000, which is bigger than the 800, which means that the y, the correct power up there, has to be between what 2 integers? 2 and 3. And because 800 is so darn close to 1,000, it's probably the y is closer to 3 than to 2. Okay? So, so our guess is that log of 800, I don't know, 2.7, 2.8, 2.6, something between 2 and 3, probably closer to 3. And now let's make sure that we can type it on the calculator. So you just hit the log button wherever it is, and then 800 and equals 2.9, as we expected. Okay? Between 2 and 3, closer to 3. Okay, so what this means is that, so what we just saw is that log of 800 in actuality is really close to 2.9 from the calculator, which means that what to the what is approximately what? 10 to the 2.9 is roughly 800. And again, that's something we can verify on the calculator. 10 raised to the 2.9, we expect it to be right around 800. So far, so good. Okay, number 4, what's the relationship between f of x equals e to the x and g of x equals ln of x? What's the relationship between those two functions? They undo each other. They're inverses of each other. That's the relationship. Okay, each other, whenever I type it into Word, I just wait for it to yell at me, and then I get it right after it yells at me. Is it 1 or 2 words? I think it's 2. Is it 2? Like I'm powerless without the stupid squiggly line underneath the thing telling me I'm an idiot. So I think it's 2. Okay, so what's the relationship between graphs of two functions that are inverses of each other? Like if I graphed e to the x and I graphed ln of x, what would I see? Yeah, the x and y values are flipped, correct. So the x and y values are flipped. Which means that the two graphs have a certain kind of symmetry, a certain relationship to each other. What happens to the graph if you just swap the x and the y point, the x and y coordinates? So the graphs, it turns out, are symmetric with respect to a certain line. That's it. Two graphs are symmetric with respect to the line y equals x. Okay, so that's probably buried someplace in your memory banks somewhere. And let's see if we can convince you of it by just looking at a picture. So number 6 says sketch the graph of the inverse of this function right here. But let's just do it kind of piece by piece. So I'm just going to start over here at this point. The coordinates of this point are -4, -3. And I know that if I go to the inverse function, that the x and y swap. That was literally the first step we did in the beginning problem, is we switched the x's and the y's. And so if I switch the x's and y's on that point, then what are the coordinates of the new point? It's -3, -4. So let's plot that point, -3, -4, which is here. So that blue point is our first point on the inverse function. Let's go ahead and take a look at this next point that I'm going to highlight. It's the x-intercept. So the coordinates here are -3, 0. And so again, if we go to the inverse by swapping the x and y, then that gives me 0, -3, which we can plot. And do you see the symmetry? Like looking at the two purple points compared to the two blue points, they are symmetric over a certain line. Do we see what line they're symmetric over? Yeah, I mean, do we buy what Andy said before, that these two guys are symmetric over the line y equals x? So if you have a straight edge handy, or maybe use the folder, go ahead and draw the line y equals x, 10, negative 10 here. That's good. And do we see the purple points just kind of flop right over onto the blue points across that line? That's what happens when you swap the x and y. You just flip the point over the line y equals x. And so we can just plot a few more points here. So for example, I won't write coordinates anymore, but that purple point, the next one is negative 1, 1, which becomes 1, negative 1. So plot the point 1, negative 1. And my next purple point here, what are the coordinates? Got right there. That's 1, 2. So it becomes 2, 1. So plot 2, 1. There. I'm going to pick a point on the purple. I'm going to pick this point right here. It's on the original graph, but it's also on the y equals x line. And I just want to highlight what happens at that point. So what are the coordinates of that point? For me, it's around 3, 3, but it depends on how you sketched it. So when you swap 3, 3, what happens? Still 3, 3, which means that I can also color this point blue. Any point that's already on y equals x doesn't go anywhere. It's already on the mirror. And then we'll just pick one more point way out to the right. How about this guy over here? Something like 10, 4. So it becomes 4, 10. So 4, 10. Okay. And then I've got 2, 4, I've got 6 points that I've labeled as blue. So if you connect them like straight where it's supposed to be straight and curvy where it's supposed to be curvy, then you'll have a pretty good graph for the inverse function. Something like that. And again, you can see the symmetry over that y equals x line. Okay, and the next problem over here, the next graph, it says sketch e to the x and ln of x on the axes below. So e to the x, we've seen this guy before, so it shouldn't take too long to graph it. It is an exponential function. Is it an exponential growth or decay? It's growth because that e is about 2.7, which is bigger than 1, the magic cutoff. Okay, and if you plug in x equals 0, what do you get for e to the 0? Is 1, so that means it goes through the point 0, 1. I think we saw that before too. And we know it's going to grow pretty darn quick over here. And what happens to the left? Close to the 0, close to the x-axis, but never actually touching. And so then I think we've already seen that the ln is the inverse. So all I need to do is flip this guy over the line y equals x. So I'll just draw that real quick. And so we'll just pick a couple of points to sort of be representative. So for example, that guy out there is roughly negative 8, comma, I don't know, like 0.1 or something close to 0, right? So when I go to the inverse function, the ln function, I just swap them. And so then the new point becomes 0.1 and then negative 8. So that guy is really close to the x-axis down here. The y-intercept was 0, 1. What does that point go to? 1, 0. So we'll plot 1, 0. And then I'll just pick one more point like this guy way up here at the top. I wasn't very precise here, so your answer is going to be different than mine. But for me, it was something like 310. You'll have a different number. But then when we flip it and it becomes 10, 3, and we get a point right around here. So then we connect the dots with some curvy, smooth thing, and we see for the first time this semester the graph of y equals ln of x. Okay, so last little bit and then activity. So there are 5 properties of logs written here. You can look at them later and use them as necessary, but I'll just point out that property C is one of the most useful. It says if you have log of something to a power, what can you do with that power? You can put it right down in the front. Right, so C is one of the most useful ones. Let's see if we can solve this problem here, number 9. 200 equals 100 times 1.01 to the 12t. That looks an awful lot like some kind of like a money problem to me. Like I see the 1.01 and I think, oh, that's just 1% growth, like an interest rate. And I see the 12t and that reminds me that, oh, maybe it's like a monthly kind of investment. And so we're trying to solve this problem here, which maybe would tell us how long it would take $100 to grow to $200 in our bank. Okay, so the goal is to solve for t. It's in the exponent, which means that anytime the unknown is in the exponent, logs are the right tool. But we don't take logs yet. First, we have to get the exponential part by itself. So that 100 is in the way. Let's divide both sides by it to just get 2 equals 1.01 to the 12t. And now that the exponential piece is alone, what do we do to both sides? We take the log. So what log do you take? Well, you could take any log you want. You could take the common log. You could take the natural log. You could take log base 17 if it floats your boat. They'll all work, but I would certainly pick one of the first 2 because those are the 2 buttons I have on my calculator. So let's just take, let's take ln of both sides. Okay, so let's use that property on the right-hand side. What can we do with that 12t exponent? Yeah, we'll bring that 12t right down in the front, just like that. Okay. Okay. All right, and then the goal is to solve for t, so we're ready to do that in one shot right now. You can get rid of the 12 and the ln of 1.01 by dividing both sides simultaneously by 12 ln of 1.01. Right? No need to do it in pieces. Let's just get rid of both. And then we'll carefully type that in. A common mistake is to forget to put what when you type this in? Parentheses around the bottom because there's 2 things down there, the 12 and the ln, both need to get divided. So parentheses around both. I'm going to use my mental calculating ability. I'm going to say about 70. Wait. No. I'm going to say about 6. What is it? 5.81. Great. Questions on that? How do you know when logs are the right tool? The variable is in the exponent. That's when we use logs. Okay. Raise a flag if you get if I can help on the activity.